Hello there. We are going to talk about the fundamental counting principle. This is where we look at how many possible outcomes we have in something. We're going to be able to represent sample spaces by using organized lists, tables, and tree diagrams. So we're going to start with that tree diagram. So let's read this. You have a photo. You want a mat and frame. You can choose from blue, purple, red, or green mat, and then a metal or wood frame. So the question says, make a tree diagram to represent all the ways you could frame this photo with one mat and one frame. So how many possible outcomes are there? So let's take a look. We can choose a blue, a purple, a red, or a green mat. So that's 1, 2, 3, 4 different mat colors we have to choose from. And then we have our metal or wood frame. So we have 1, 2 different ways we can frame this. So let's basically start with our project here. And then we can choose one of 4 different mats. So 1, 2, 3, 4. So we have blue, purple, red, or green. And you have to be careful because these branch out pretty fast, okay? So we usually keep our problems with these pretty small. Now, once we pick a mat, now we have to pick a frame, either metal or wood. So if we get a blue mat, we have 2 choices, metal or wood. If we get a purple mat, we have 2 choices of frame, metal or wood. Red mat, we have 2 choices, metal or wood. Green mat, 2 choices of frame, metal or wood. Okay? And I really want to make sure we understand tree diagrams because we're going to learn a shortcut here in just a few minutes for figuring out the total possibilities. However, when we jump ahead a couple probability lessons, we will be using tree diagrams to actually help us calculate the probabilities. So we're going to get to a point where we're going to be putting decimals on each one of these branches. So we want to make sure we understand how to set them up in the first place. So it looks like we have 1, 2, 3, 4, 5, 6, 7, 8 different ways. There's 8 possible outcomes. And you may encounter questions at some point that would make you list them all, and you would usually do that with a code where you would have like a blue with a metal, a blue with a wood, a purple with a metal, a purple with a wood, a red with a metal, a red with a wood, green with a metal, green with a wood. So you may see annotations kind of like this as well, okay? But it turns out there's a shortcut here, and some of you looking at the numbers 4 and 2 may have already figured this out since we came up with 8. I wonder how we mix together 4 and 2 and get 8. Such a debate. So that's where we come to this fundamental counting principle, and it's a shortcut that we can use when we have a large number of outcomes. So this wasn't too bad to make a tree diagram for 4 frames or 4 mats and 2 frames, but if we were to start doing license plates and you have 26 letters to choose from and 10 numbers for every different spot, and maybe you're going to have a 6-digit license plate number, trying to do a tree diagram with 26 letters of the alphabet and then another 26 letters of the alphabet, etc. is very time consuming and painful. So we want to understand this. So if we have m possible outcomes, and a second event has n possible outcomes, so that would be like 4 possible mats, 2 possible frames, the total outcomes is just m times n. So if you go back, if we had 4 possible mats and 2 possible frames, multiply them to get 8. So pretty easy. So let's take a look at a question. Andy's planning a special date for his girlfriend to celebrate her birthday. Good man, Andy. When he picks her up, he will give her either candy or flowers. So first thing, candy or flowers. So there's 2 things there, a little gift to start the evening off on the right note. For dinner, he will ask if she will prefer to go to Mexican, Chinese, seafood, or Italian. So it looks like he's going to give her 1, 2, 3, 4 different restaurant options. Ooh. And then they will do a fun activity. And he's thinking in terms of putt-putt, bowling, or the movies. 1, 2, 3. And now Andy's going to have to be a little bit careful here because on the one hand, he wants to make his date happy, but on the other hand, he doesn't want to have to make her do all the thinking or the work because that may also irritate her. So you got to play this by ear a little bit, how much Andy decides on and how much he asks her to handle because She doesn't want to plan her own birthday party. Let me just put that out there for you. Okay, so basically we have a gift. We have 2 options for the gift. Then the actual meal, we came up with 4 different options. And then for the fun afterwards, we came up with 3 more options. So 2 times 4 times 3 gives us a total of 24 possibilities for a fantastic birthday date night. Okay, so there we have it. All right, so now we're actually going to use this little strategy to find some probabilities. So let's take a look. I taught you about license plates already. License plates are being produced that have a single letter followed by 3 digits. So license plate could be like A123 or Z745. Okay, so 4 different positions in the license plate. Okay. So use the fundamental counting principle to find the number of possible license plates. So keep in mind, and I like to come up with a code, we know we're going to start with a letter, and then we're going to have a number, and a number. Okay? So when we think of the letter, we have 26 different letters in the alphabet, so 26 options to go in that location. And then keep in mind that each one of these is a single digit. So basically, if we could put 0, 1, 2, 3, 4, 5, 6, 7, 8, or 9 in those places. So that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 different possibilities to put a single digit in each location. So in the second place, we could put 10. In the third place, we have 10 options. In the third place, we have 10 options. So basically, we take 26 times 10 times 10 times 10. We end up with 26,000 possible license plates. Okay. And that's for a pretty small license plate number with just 1 letter and 3 digits. So now we're going to find the probability that a license plate has the letter Q. Now, a couple different ways you can think about this one, okay? Really, all we have to look at is this number right here. So there's only 1 Q out of 26 letters, so we could say the probability would be 1 out of 26. Or you could think of it in terms of there are, if we look at those 4 different places, right? There's only 1 way to get a Q, and then we still have 10 different ways to get all the numbers here. So really, that's 1,000 different ways we could do it out of the 26,000 total possibilities. And of course, if we reduce that fraction, we get back to 1 out of 26. So I personally like to simplify it and not even worry about the numbers in this one, but I think it's good for us to understand both ways. Okay. Now, let's find the probability that a license plate does not contain a 3. So let's take a look at this. Now let's go back to the original license plate. I said we're going to have a letter, and then we're going to have a number, and a number, and a number. Okay? Now let's think about it. If we only look at the numbers, now no 3, so if we look in this position, out of the 10 possible numbers we could put there, 9 of them are not a 3. So there's 9 different things we could put in this location to not have a 3. Same thing here. There's 9 different ways we could not get a 3, 9 different ways we could not get a 3. And I'm really not even going to worry about this letter because we don't care right now. Okay, it's just like up here, the simplified version. So 9 times 9 times 9 is 729. 729 different ways, basically out of 1,000, because if you look at the fact that there were 10 different numbers you could go. So you could say 720, oh, I'm missing a number there. 729 out of 1,000, that's also 0.729 or 72.9%. Probability we haven't mentioned yet, but you can do it in fraction form, decimal form, or percent form, okay? And then let's take a look. Find the probability that a license plate contains exactly 1 3. Well, let's take a look at this. We have a couple different ways we could do that. We have, again, I'm not even going to worry about the letter. I'm just going to focus on these numbers, okay? So we have some different situations. We could have a 3 as the first number, and of course, if we do, then if we only want to have exactly one 3, the second number would be something that's not a 3, and the third number would be something that's not a 3. So when we do that, there's one way to get a 3. And then if this one's not a 3, there's 9 ways to get not a 3. And again, 9 ways to not get a 3 again. And of course, that's out of 1,000. Okay, because we started with 10 possible ways to get 3 numbers in a row. Okay, so 81 out of 1,000. Now we're going to have to add to that the other possibilities. Okay, we could have some number that's not a 3 in the first location, a 3 in the second location, and some number that's not a 3. And it turns out the probability of getting that is the same as this. So we know there's 9 different ways to get not a 3, 1 way to get a 3, 9 different ways to get not a 3. And that's, again, out of 1,000 different ways. And notice I'm ignoring that letter because it doesn't matter at this point because we can end up reducing the fraction. And then the third way to get exactly 1 3 would be some number in the first digit, some number that's not a 3, and then a 3. And again, 9 ways to get not a 3, 9 ways to get not a 3, 1 way to get a 3. And again, those are out of 1,000. And if we add up, those are all 81 out of 1,000. That turns into, whoops, you can't even see that, sorry, 243 out of 1,000. Okay, so there's just some examples about how that works. You can also list that as a decimal point 243 is one way, or 24.3% is the probability of, you just go in and you just say, hey, I want a license plate. What's the random opportunity that they're going to hand you one that has exactly 1 3 in it? All right, so now I want you to do some thinking. This goes back to the fundamental counting principle. You're going on vacation. You pack 2 pairs of pants, 3 shirts, 2 sweaters for your vacation. This gives you a total of 12 possible outfits because 2 times 3 is 6 times 2 is 12. You have room in your suitcase for one more item. You're looking at it, you have this little compartment of space just right over in the corner, like I could stick one more thing in there. And so what I want you to think about is what should you stuff in that little spot? Another shirt or another pair of pants, and why? I'm going to tell you, the winner is the pants. Okay, because of right now, you have 2 times 3 times 2. And remember, this was pants. This was shirts. And this was sweaters. Okay, so if we add an extra pants plus 1 pants, we now have 3 pants, 3 shirts, and 2 sweaters, and that gives you now 18 outfits. If you add a shirt, you would have 2 pants, 4 shirts, and 2 sweaters. 2 times 4 is 8, times 2 is 16. So adding the extra pair of pants gives you more possible outfits to wear on your vacation. How awesome is that?